morning. Small group today. I just finished designing the problems for the exam. And as a little reward for those who are here, we are going through these exam problems now. You don't believe that, do you? The stream will be awkward today, and I'm sorry for that, because the camera settings have been changed again and fixed. And so all you see in this, well, all I think you can see in this in the stream are the boards. Can't change it right now. All right. Do you have questions? I didn't prepare anything. If you don't, it's not a problem either. It's just an offer. Yes.
When we were dealing with stability analysis, we used the Bernoulli equation where we assumed that the flow is rotational. The linearized Bernoulli equation. You know what?
I know what you mean. I just don't get the connection to stability analysis because, okay.
You used it there, it's just one example.
Okay, yeah, go ahead.
How do I know that I actually deal with a rotational flow? If it's not given in the problem sheet, like in practice.
Then you have a problem. Let me go there. There must be somewhere around here. So you're referring to the time-dependent Bernoulli equation, are you? We are approaching, I think. Indeed, yes. Okay, so that's the time-independent part. And if you do have time dependence, you arrive here, right? And you are referring to the problem that we have introduced a velocity potential there. All right, and your question was, what do I do if there is a curl, if there is vorticity?
And how do I decide when I was looking at the problem that there is no vorticity?
I don't know. So what I'm going to say now are attempts, right? So usually Helmholtz theorem tells you that you can decompose any vector field in 3 dimensions into a gradient and a curl. So then I would split up the velocity field into both, and then equation 3, 3, 11 here would still apply to the gradient component. So you can separate this, and then you know the rest will deal with the curl component only. And with that I would go back to the original equation and see if I can deal with that. That's a tentative answer. Don't necessarily trust it. Yes?
Rotating cylinder it was just given that it wasn't compressible. So we just know stage one because of the circumstances, logical.
Yeah, because the situation doesn't change.
Yeah.
So it's a situation where the whole setup is time independent, and yet things are moving. So it's a stationary but not a static situation. Let's see. Must be around here, I think. Somewhere here? Sheet 7. Okay. Now here everything is derived. Well, VR is 0. So because of that? No problem. Could it be another?
Possibly, but I don't know which one. It's not too important.
I think it's the only one that is related to what you're asking, but that was a nice one, wasn't it?
It wasn't like widespread next to it. I wasn't sure that the correction term was alpha T. And I think my exercise was they didn't know what to correct it. Because we have to be straight.
Why is the correction term alpha T?
Because I took the given Barnard's equation and took as correction from every term that's in addition to the ideal gas.
All right, let's see, what's the problem? It was shown in the lecture that the sound speed at constant entropy is this. All right, yes. So if you had an ideal gas, this equation here, Cs square equals, and so on, that would just be Cs square equals gamma p over O. So alpha t is what changes this possibly away from the ideal gas situation if alpha t is not 1. So the first part of the problem is to show that alpha t is 1 for an ideal gas, and then just falls back to the previous situation. So then the question is, what is alpha t for anything else? And blah 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 blah, calculation, and then you arrive here, and you see that for air, for example, alpha t is not 1. That's true. But almost 1. Yeah, okay. That was meant to be the point.
I've got one other question regarding the averages in sheet 10. Could you write them out? Because I wasn't quite sure.
Sheet 10. Let's go to the solutions immediately. So, what problem are you in? All right. So let's go through that. So the situation is that, okay, fine. Since Faraday rotation is only sensitive to the line of sight component B parallel of the magnetic field, it can only measure a net magnetic field remaining after cancellation of sections along the line of sight where the field is pointing towards or away from the observer. So the idea is, suppose you have a magnetic field line like this, right? you will only see that part of the field line that is parallel to the line of sight in the Faraday rotation. All right, the rotation measure is given by this, and the parallel direction is called the z direction now. Okay, now the questions are, what is the expectation value of the rotation measure created by a randomly magnetized homogeneous medium? That was meant to be a warm-up, and obviously that's 0. Okay, what is the variance of the distribution of rotation measures obtained along many different lines of sight through the randomly magnetized medium if the energy density in the magnetic field is UB and the lines of sight have a length L? Okay, so there the idea is that you have this randomly magnetized medium, and you poke lines of sight through that. And then you will have a mean, this is what we just calculated, and the mean is 0. But you also will have a variance. What is that variance? So the idea is that you calculate this thing. And so this would be this. That goes away. So that remains. And then you see in the integral for that, you get a b square. And okay. I'm averaging over light rays. So as the setup is, here's the direction of the lines of sight. Somewhere here's the thing we're looking at, and now light rays go through that, and the average will be this. Okay, so you take n light rays, you shoot them through this medium, and you get this. And the light rays will differ only by their x and y coordinates. So what you essentially do is you carry out an average over different positions, xi, yi, of the light rays in projection here.
Will the values by symmetry interpretation get the di's rated back to 1/3 of the expectation value?
Yeah.
The expectation value is over the expected value of b squared, which can be related to UB, is over all coordinates, right?
Yeah. So the idea is that here you have your xy coordinate system, and you have random positions through that plane, and then the rotation measure squared will be formally this thing here. If you had different lines of sight. But now, since you're looking at one specific line of sight, this turns into that. We have assumed a homogeneous medium, so independent of the coordinates of the x and y coordinates of the light rays, NE squared will always be the same. And so the question is just, what is this? And now we have assumed a randomly magnetized medium. So this would mean that the BZ square values along each line of sight would be independent. And then you can split up this average, and everyone will give you the same. That's average over the lines of sight, exactly. So what we meant by that is this expression here.
Yeah. How do you get the average of the line of sight to be average? Like, is the average of a p squared the average of a line of sight, or the average of the whole?
So that would be the variance for a single line of sight. And then once you take the average, you would have to replace this by this expression. Now, since they are all independent, this would just be n times the average squared divided by n. So that would be a third of the energy density times 4 pi. So that would be this. Right, because this, and since it's assumed to be isotropic, all coordinates must contribute the same value.
When do we take the average? Like, is this
Here. That's the average. Mirko, yeah?
I'm also wondering, how can we treat the BT square on the same, to be on the same line, even though we are taking the average over all the different line of sight?
Careful. We are not averaging between lines of sight, but we are averaging the square of the rotation measure. So we are not taking rotation measure here times rotation measure there, but we are taking the square here, the square here, the square here, and so on.
I would find the most interesting. The average of a piece is an average not with respect to an average not with respect to the line of sight, but with respect to the whole sphere system. Like,
It's the same thing. So this is the situation we had in mind. So in projection, in the xy plane, these are the light rays. So the average over different positions, or the average over light rays, are the same thing. I choose random positions here.
average only over x and y. And I thought the average down there is over x, y, and z.
No, it isn't.
Okay.
That's an average over light rays.
Okay.
And each light ray gets its complete signal from an integral along it. So the z component is out because we integrate over it. And then each light ray picks up a signal according to its xy direction. Now, under the assumptions that we have made, that we have random fields, or in other words, an uncorrelated field, which is statistically isotropic, then there must be a factor of a third due to the isotropy, and all these averages must be independent. So this is just this. On average. If you have a small sample, that wouldn't work out. Does that make it clear? not completely. What's missing?
And we don't always take the average with left side, right? We sometimes take the average with respect to all corners.
You can do this similarly.
And I thought that was what we meant by average over respect.
You can turn this into an average over lines of sight. If you take that and normalize by the area. If you do it this way, you pretend that you have infinitely many light rays. If you have a finite collection of light rays, you would have this density of light rays there. So you can, in this way, you can connect the two. But if you had a continuum of light rays, in other words, a light bundle, that would be the integral over the coordinates. And yeah, if you dissolve the light bundle into individual rays, you're back here. Now good? Yeah. All right. This is also how this correlation function in the next part of the problem comes into the game, right? Because once they are correlated, they are not independent anymore, and then the correlation function enters. All right.
Also highly specific. In the online quiz to plasma physics and to hydrodynamics.
The online quiz?
Yeah, on the first question.
Wait a moment. Let's get there. How do I get there? Online tests. Yes. Here we go. On plasma physics?
Yes.
Mm-hmm. Which one?
The first one.
The first one. Wait. What is a good display?
Also the lightest one, so it's like hard to see.
Okay, well, I think we can deal with that. Thermal plasmas are characterized by several scales, largely determining their properties. Which of the following statements are correct? Now.
Yes. One of the options is the Debye wavelength is a typical wave for typical wavelengths of sound waves in the plasma. I see that this is not how it's defined, but I don't see how we can exclude it from also doing that. Like, is this related to the plasma frequency, which we can somehow relate to sound waves? So one could argue that it's somehow also, but yeah. And the more we talked about it, the more confused we got, I think, so I'd like some clarity.
Okay, so if you want to address sound waves in the plasma, you would return to a neutral gas, in fact, because the electrons and the ions are tightly coupled. And then the dispersion relation for ordinary sound waves would give you the wavelength of sound waves in the plasma. And that has nothing to do with the Debye wavelength. Right? Because this just depends on density and pressure. So that was the idea behind that. Now you can have additional types of sound waves in the plasma. For example, the ion acoustic wave that we talked about, where you do not treat the plasma as a tightly coupled gas of two different species, but where you take the possible oscillations of the electrons against the ions into account. And then the Debye wavelength does enter, that's true. But if you, as long as you treat the plasma as a continuum with tightly coupled species, those sound waves have nothing to do with the Debye wavelength. Yeah. Ion acoustic waves is a different story. Yeah?
Question related to that. What is the relevance of sound waves in an astrophysical context? How do we measure them? How is it related to electromagnetic radiation?
Mm-hmm.
We talked too much about sound waves. I don't have a question.
Yeah. What was the first part of your question? I didn't get that.
Relevance of sound waves in an astrophysical.
Relevance. The relevance. All right. First of all, what I wanted to show when we talked about sound waves for the first time was that sound waves deepen and form shocks. And what we needed for that was that the sound speed increases as the density goes up. That was the most important part, right? There was a motivation for the occurrence of shocks. And then, in the further discussions of sound waves, I derived the dispersion relations so that you can see when the sound waves would become unstable, and when they would lead to instabilities. Sound waves are important whenever you can. Let me start with an example. People can measure sound waves in stars. How do they do that? They do harmonic decomposition of the brightness on the surface of the star, or of the velocity on the surface of the star. And then you find that there's a pattern imprinted caused by sound waves propagating within the star. These are standing sound waves in the star. And they give rise to a certain pattern, and then you can decompose that pattern and use that to diagnose the interior of the star, because that will show you which waves can propagate within the star and which waves cannot. And this tells you a lot about the internal structure of stars. So I would say the first part of the relevance is they can turn into shocks. The second part of their relevance is they can become unstable. And the third part is they are a diagnostic for the interiors of stars, for example. And that has solved a lot of problems, for example, that we had with, for example, the energy transport within stars. Is it through convection? Is it through radiation? What's the composition of the, at what depth in the star, and so on. So yes, they are pretty relevant. In particular, of course, if they become unstable. Yes, you ask for the relation to electromagnetism. Well, they would make the medium fluctuate through which electromagnetic radiation will propagate. Therefore, they will create fluctuations in intensity, for example. Other relations. If you had sound waves of two different species in a plasma against each other, for example, then you would also excite electromagnetic waves through the oscillations of the charges. Others? I'm not sure about that. Yeah, all right. Yes.
Maybe also connected to the sound wave. I wasn't quite sure. So when we discussed the steepening of sound wave, before that we discussed the method of characteristics.
Mm.
And I wasn't quite sure how we connected both these topics. So how did we get from the method of characteristics to the steepening of sound wave?
Mm. The idea was that in a previously unperturbed medium, you suddenly create a pressure perturbation. And then you want to know where does this pressure propagation travel to and how fast does it do that. And in that situation, you can always connect the point in question to an unperturbed point in your gas distribution through one of the characteristics, and then you know that along this characteristic you will have a Riemann invariant. So this is one way to identify physical quantities along characteristic lines. That was the point. And in the situation that I had in mind, or that I wanted to describe, you can follow these characteristics backward into unperturbed matter, into unperturbed medium, and then you know all about your gas that you want to know. That was the point of that. And apart from that, the method of characteristics is pretty nice, isn't it? Yes.
I wasn't quite sure. So in the synchrotron spectrum, we also introduced a cutoff frequency. Where did that come from again?
Synchrotron. Wait a moment. A synchrotron radiation. Okay. This one you mean, right? Where the spectrum falls down. It automatically comes out. Why does it do that? Because these fractional order Bessel functions here have an exponential cutoff. Okay, so where do these Bessel functions come from? And if you go through that, you see there are these integrals here over this phase. They immediately lead to these Bessel functions, and they give rise to the exponential cutoff. And ultimately, the occurrence of the cutoff has to do with this form of the phase here. And this is due to our second order Taylor approximation that we made. Or in fact, it's a third order Taylor approximation. So why could we do that? We could make this third order Taylor approximation because we knew that the signal will only come from a very, very limited part of the orbit, right? While this radiation cone will move across you. So essentially, this is a consequence of the finite duration of the signal, right? If the beam was infinitely sharp, it would be a delta function in the time domain, and therefore a constant in the frequency domain. So you see, this exponential cutoff comes because the beam is very sharp, but not infinitely sharp. All right? Bessel functions traced backwards. Okay. Yes.
A very broad question, perhaps, in the plasma physics chapter again. We have the two chapters, waves in the phase called plasmas and hydromagnetic waves. Could you perhaps just briefly say how the results we find there are connected? Because I don't have a good overview there, I think. Because we, in both cases, derive dispersion relations, but...
All right, okay, so you are speaking about sections 4.8 and 4.9. Let's go to 4.8 first. This concerns the propagation of electromagnetic waves through plasmas. So that has to do with plasma perturbations. In fact, what we are looking at here is the perturbation of the electron density only by electromagnetic radiation. That's that. The other part, hydromagnetic waves, they are perturbations of the plasma density itself. Plasma density and velocity and so on. So in one case I'm asking how do electromagnetic waves propagate through the plasma? And then you find these restrictions that we found. The other question is if I perturb, or if I place, let's say, a pressure perturbation into the plasma, how would that propagate through the plasma? So that's a different story. So one thing has to do with the stability of the plasma itself against perturbation, and the other one has to do with the propagation of light rays through the plasma.
In my understanding, they were somehow related because the magnetic field is frozen in and they're tightly coupled. So are they connected or are they just completely separated?
The way we treated them makes them appear completely separate. Right? Because when we spoke about the hydromagnetic waves, we speak about a single density and a single velocity. But the propagation of electromagnetic radiation through the plasma requires that you shake the electrons but not the ions. So the way how we treated it makes them appear disconnected. If you now would apply the same stability analysis that starts with 4286 here to the two species separately and take into account that they again are coupled with each other, then you would see, that's the next order of the procedures, then you would see a connection between them.
So we just didn't do that, essentially?
We didn't do that, no. I thought that it was complicated enough. But from the fact that we treat the plasma with a single density and single velocity here, you see that we are not distinguishing species, and therefore you cannot see a connection between the propagation properties and the hydromagnetic waves here. I was thinking for a while that we should introduce theoretical astrophysics part 2 into our curriculum. There is quantum field theory 2 as well, right? But then the observational astronomers complained because they said then we would have to introduce astronomy 2 as well. Right? And they didn't feel like doing that. So for political reasons, there's only... Okay, good. Yes. All right, in general that's a difficult question because you can create polarization from completely unpolarized light, as we discussed on Monday. And if you irradiate Thomson scattering charges with a quadrupolar intensity fluctuation, the outcome will be about 10% polarized, just because of the anisotropy of the scattering cross-section. So this means that you can turn an anisotropy of unpolarized light into partly polarized light due to the anisotropy of scattering cross-section. Generally speaking, however, you can get strongly polarized light only if you have some preferred direction in your medium that orders the motion of the accelerated electrons, and that would be a magnetic field. So typically you will create strongly linearly polarized light if you emit light in the magnetic field. And then if the magnetic field is ordered over large length scales, you can create large amounts of polarized radiation. If the magnetic field has a short correlation length, right? If it changes direction all the time, it won't be polarized either. So this means that if you have created polarized radiation this way, and you go through a medium that itself is not ordered in any sense, it will depolarize the radiation again by emission, by absorption and re-emission of the radiation. All right. Another polarizing effect is due to reflection on media, but this is typically a very weak effect. So magnetic fields are your bet. Right? Once you have polarized radiation, it's extremely valuable because of Faraday rotation and because you essentially trace the orientation of the magnetic field in that way, and so on and so forth. And so you have very carefully made polarization maps, for example, of nearby spiral galaxies, where you see the ordering of the magnetic field in spiral disks and so on. Do we have anything else? Yes.
In one lecture, we derived the disk potential.
That was the streamed lecture. Yes.
Yeah.
How awkward was that?
I tried to reproduce the result using the Green's function of the Laplacians, because that's how I would try to solve the equation.
Aha. What Green's function did you take?
Yeah. Which Green's function?
Yes.
The Laplacian in 3 dimensions.
In 2 dimensions.
No, first of all, 3 dimensions, and then I used the integral representations with the coordinates.
Ah, careful.
I didn't get far.
Yeah, no surprise. The Green's function for the Laplacian in 3 dimensions, as you know, is just given by 1 over k squared in Fourier space, and then you get the retarded potentials and so on. For the 2-dimensional Laplacian, it's the logarithm. The Green's function is the logarithm. And then we have a mixture here between, since we introduced cylindrical coordinates, you know that the solutions of the Poisson equation must be linear combinations of eigenfunctions of the Laplacian in 2 dimensions and of the Laplacian in the Z component. And this is why you need to be very careful in constructing a Green's function there. It's easier to decompose the solution into linear combinations of eigenfunctions, because then you have instantly the cylindrical Bessel functions and the exponentials.
I still don't quite get why I can't use a 3-dimensional Green's function, because like density is 3-dimensional, just restricted by the delta function to the z equals 0 plane. Why can't I
can't you do that? So essentially you're suggesting a separation ansatz, right? And so you would say you have a two-dimensional part of your Laplacian. Like that, right? And this would be something like this, right? It should be a bit more explicit. Let me write R for the cylindrical radius. So you would make a separation ansatz like that? Is that what?
I would treat the Laplacian on the left-hand side as the ordinary 3 Laplacian that it is.
Okay.
Then I would take the Green's function, so I get the integral of sigma and the delta distribution over the distance, and then just restrict myself to z equals 0 in that integral.
Uh-huh. Not very beautiful, but so that's what you want to do. Yeah, why not?
But this is possible. Then I got to introduce one Bessel function using that as the integral representation of 1 over x minus x prime in cylindrical coordinates. That's the Bessel function. Then it looks quite similar already. And it is far from it.
So we'd use that, and what I would instantly do would be to integrate the z coordinate out. And then you would have this, right? That should equally work, yeah.
Yeah, and then I was wondering how it would turn this expression into the one we derived from H. They must be equal, but one point I didn't really see how.
Next thing I would do would be to introduce cylindrical coordinates here. This leads you to the representation with in terms of the cylindrical Bessels, and then you need to use completeness relations of the Bessels, I think. I didn't do this. I didn't do this ever. But I wouldn't see why this shouldn't work. According to this recipe. What I found easier was to just span the sigma delta z by eigenfunctions of the Laplacian, and then you're immediately there.
Yeah, after doing this calculation, I thought why we did it the way we did it.
It's worth a try. I'm going to try this as well. Yeah. All right. But there's no problem with that solution path. I mean, this must work. Anything else? You would have time to go through the exam problems. All right. If you are satisfied right now, I think we conclude that. While you will be, yeah. Go ahead. Of the equivalence between what?
Equivalence that we use for the term growth.
Ah, okay. That's just the area covered by a spectral line. So you have a spectral line like that, and the equivalence width is the width of a rectangle whose area is the same as that taken away by the spectral line. Good. While you will be writing the exam next week, I will be in 2 different doctoral exams. Exams all around. So I'm not going to be there. But of course, our head tutor, Michael Zacharias, is going to organize the exam. We are about to finish the problems. The subjects are very clear. I'm aware that the same afternoon, so Thursday afternoon next week, some of you will have the QFT exam. This is an unfortunate coincidence. But that much I can tell you, that the problems for the exam will be very close to problems that you have already seen. Now, I gave you the following hints. The first hint is there were 5 sections in the lecture. Apart from comprehension questions, there will be 5 problems on the exam sheet. You can pretty well imagine from what fields of the lecture they are going to be. Okay, so there will be 1 problem in radiation and so on and so forth. There are not so many of these problems that you have seen on the problem sheets that are suitable for the exam. I mean, for example, we can't confuse you with many hints, and so on and so forth. So I think it's not too difficult to guess which problems. I should stop. Michael will be angry at me. Sorry? Yeah, sorry. Yeah, you will have comprehension questions. So the first part will be comprehension questions, I think 5 or 6 of them, where you can, that will be multiple choice, as you know, or as you have seen them on the problem sheets. And apart from these comprehension questions, there will be 5 problems to calculate. 1 from each section. Approximately equally weighted.
Will the choice questions only have 1 right answer,
You're asking for a lot, Mirko. I'm not sure yet. Probably each of them will have a single correct answer. And we are not going to count wrong answers against you. It's just that we will not count wrong answers, full stop. So there will be no negative points. I find negative points really awkward. They will be similar to similar but easier than the questions I ask in the quizzes. And the division of the lecture into 5 pieces suggests 5 comprehension questions. 5 is the number thou shalt count to. You know the Monty Pythons. 3 is the number thou shalt count to, and the number thou shalt count to is 3. Okay. You know that? The directions for using the holy hand grenade of Antioch. We should stop now. All right. Thank you very much for your attention. I had a lot of fun with this lecture. I hope you too. I purposefully did not look at the evaluation results yet. I'm good.